Welcome everyone to week 5 of the PMRF TA sessions for the NPTEL course Electronic Properties of the Materials Computational Approach. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Soil State and Structure Chemistry Unit SSCU of the Indian Institute of Science IISc Bangalore, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL PMRF TA for this course. And we are having total 8 2-hour interactive problem solving sessions every Friday from 7 p.m. to 9 p.m. as a reminder. And today we are going to start our 5th session in this series. So in this session what we are going to do is we are going to solve some problems, some numerical problems that we were not able to complete in the last 4 sessions. So we will be solving some problems related to week 1 to week 4 content in this session. And then we will also solve the coding problem from the assignments that have been submitted. Mostly we will solve just the week 1 and week 2 coding problems. And in the next session we will start with week 3 and week 4, week 3, week 2, week 5 coding problems will be solved in the next session. And accordingly we will also solve some numerical problems from week 5 and week 6. Alright. So let's just start with our session. So let me just start with problem number 1. Alright, just 1 minute. Okay, let me just check if the recording is alright. So we will start our problem number 1, and our problem number 1 is basically the problem number 4 from our last session. So we were not able to complete. We have completed the A and B part of this problem. The C part was remaining. Sorry. Okay. So let me just go through the problem again. So what we are given is that we are given a hexagonal space lattice, and for that hexagonal space lattice we have provided this primitive lattice vectors A1, A2, and A3. All right. So A1, A2, A3 were given to us. First, what we had to do is we have to show that the volume of the primitive cell was this. So we know that the cell volume is given by this A1 vector dot A2 vector cross A3 vector, and here is A1, A2, A3 vector were given to us. So we just solve this volume problem. We just put this A1, A2, A3 values in this equation, and we solve this cross product. We use this identities, the dot product of x cap, y cap, and z cap, and the cross dot and cross product of this unit vectors, Cartesian unit vectors. And using that we calculated this dot and cross products, and we found that our volume was root 3 a square c by 2. Alright. Then in the B part it was asking that we have to show that the primitive transitions of the reciprocal lattice vector are given by this B1, B2, B3. So for the B part we went, and also B part was not only this, and also we so that the lattice is its own reciprocal but with a rotation of axis. So basically in the B part what we had shown is that first of all we find this B1, B2, B3, and we had shown that B1, B2, B3 are given by these formulas. And then we also had shown that the reciprocal lattice of a hexagonal space lattice, that is also a hexagonal space lattice, only rotated but with a rotation of axis. Alright, so this is the B part. So we know the formula for B1 vector. From part A we know that E2 vector, and from we just solve using this formula, which is 2 pi times E2 vector cross theta divided by A1 vector dot E2 vector cross C3 vector. We solved for B1 vector, and then this part I left it for you to find the B2 vector and B3 vector. It is just the same. So like to solve this problem for the B2 vector, again you just have to use the formula. B2 vector is equals to 2 pi times. So let us just in this session let me just give you the solution for this B2 vector as well. Okay, so just for a revision. Now in this B part, if we have to solve the B2 vector, okay, so B2 vector will be equals to, as we know by formula, it will be A3 vector plus A1 vector divided by A1 vector dot A2 vector cross A3 vector. Alright. Now what we need A3 vector cross A1 vector. I don't think we have that in here, but we have the volume, which is A1 vector dot. Okay. Alright. We didn't find the A2 vector. Okay, now So here again now our even vector. So here we know that our even vector, what was our even vector? Our even vector is this root 3 a by 2 x cap plus a by 2 y cap plus a by 2 y cap, and our a3 vector, that is given by, so we have to so for b2 vector it is given by 2 pi m e3 vector plus a1 vector divided by a1 vector dot e2 vector plus a3 vector. Alright, and our b3 vector, that is e3 vector, it is given by c times of the z cap, c times of z cap. So from here first and also we know that even vector dot e2 vector cross a3 vector, that is we have found, which is basically the volume. Okay, you just take the modulus value in this, and in this case what was the value? We got the value as root 3 by 2 a square c, root 3 by 2 a square c. Alright, so this also we already know. So now so only thing I guess we have to find is e3 vectors cross a1 vector, so let's just do it. So here e3 vector cross a1 vector, this we need to find. Our e3 vector is c times of z cap, and we have to take cross product root 3 a by 2 x cap plus a by 2 y cap, and you can see from the identity that is given, so this way just gives us root 3 ac by 2 z cap cross x cap. This we have to solve, and then we have c a by 2 z cap cross y cap, and this z cap cross x cap, if you go back to this identity, so z cap cross x cap is y cap, okay, and z cap plus y cap is minus x cap. Okay, this two you can see here, right? Z cap plus x cap y cap, z cap plus y cap is equal to minus of x cap. So these values we will put here. So from here we have root 3 ac by 2 z cap plus x cap will be is equals to y cap plus I will have c a by 2, and z cap plus y cap will be equals to minus of x cap. Right, so this will be my answer, and thus my b2 vector will be equals to I will just use this x cap first, minus ca by 2 x cap plus root 3 ac by 2 y cap, and we have to divide by even vector dot e2 vector plus a3 vector, which we know is root 3 by 2 a square c, right? Root 3 a square c by 2. So root 3 a square c by 2, just put it here, root 3 a square c by 2, and thus our b2 vector. So if I calculate it here, this ac values will cancel out, right, and ac by 2 will cancel out from here, so I will have minus 1 by root 3a times x cap plus here root 3 ac by 2 will cancel out, I will have 1 by a y cap. So, let me just check. This is the answer that we should have got, minus 2 pi by root 3a x cap 2 pi by, okay, how, yeah, I forgot, okay, yeah, there is a 2 pi also multiply, okay, I forgot that, so there will be a 2 pi as well. In the formula, remember that the formula is 2 pi times a3 vector, I forgot 2 pi, so minus 2 pi by root 3a x cap plus 2 pi by a y cap plus 2 pi by y cap. Okay, so this we have root. Okay, so this is for the b2 vector, and similarly we have to find our b3 vector as well, and for the b3 vector as well the solution will be similar. We just need to remember the formula. So the formula for b3 vector will be 2 pi times e1 vector cross e2 vector divided by e1 vector dot e2 vector cross e3 vector. Alright, and again we will just now again what we have, e1 vector is given to us, e1 vector is root 3a by 2 x cap plus let me just first. So yeah, so okay, so it is root 3 by 2 x cap plus a by 2 y cap, and we have our e2 vector, that is equals to minus root 3 a by 2 x cap plus a by 2 y cap, and we have e1 vector dot e2 vector cross e3 vector Okay, that is that we have found in our part A, and that is equals to root 3 by 2 a square c. Alright, the same thing. And now again how we will do it, we will solve first e1 vector cross e2 vector to find the v3 vector. Okay, we just have to solve that, and the denominator is already we have solved. So e1 vector is root 3 a by 2 x cap plus a by 2 y cap cross product minus root 3 a by 2 x cap plus a by 2 y cap. Alright, now from here what we will have minus 3 a square by 4 x cap cross x cap, and then I have plus root 3 a square by 4 x cap cross y cap, and I have minus root 3 a square by 4 y cap cross x cap, and we will have plus a square by 4 y cap cross y cap. And here this x cap cross x cap, that will be 0. So this this will be 0, and this y cap cross y cap will also be 0. This we know this will be equals to z cap, and this will be equals to minus of z cap. So what we will have? We will have root 3 a square by 4 z cap and minus of plus root 3 a square by 4 z cap. So basically what we have is root 3 a square by 2 z cap. So our b3 vector will be equals to 2 pi times this e1 vector cross e2 vector. Alright, and that we have found it to be root 3 a square by 2 z cap divided by e1 vector dot e2 vector cross a3 vector, which is root 3 by 2 a square c, and thus our b3 vector will be equals to 2 pi times root 3 a square by 2 will cancel out from both sides, so we have 2 pi by c z cap. And as you can see, this is what we had to prove in DIY I left earlier. It is 2 pi by c z cap. Okay, so we have solved it as well. And then what we have shown is that this a3 vector and b3 vector, they are both along the z axis, and in the xy plane the lattice and the reciprocal lattice are as shown, and in the xy plane the lattice and the reciprocal lattice are as shown below. Okay, so in the xy plane we can see that this a1 vector, a2 vector, they also form this hexagonal lattice, and b1 vector, b2 vector, they also form a hexagonal lattice, and a3, b3, they are both in the perpendicular direction. So our reciprocal lattice is also a similar hexagonal lattice. By looking at above figure, obviously the reciprocal lattice is also a hexagonal lattice, but with a rotation about the z axis by an angle 30 degree. Okay, by an angle 30, which I have said that it will be the angle a1 vector, b1 vector. So how you find the angle between a1 vector and b1 vector? So let's say theta is the angle between a1 vector and b1 vector. So cos of theta will be equals to a1 vector dot b1 vector divided by mod of a1 vector and mod of b1 vector. Alright, so now we have to just do a dot product of both of them. Now here a1 vector, as we know, okay, let me just write both the a1 vector and a2 vector. Now a1 vector is given to us, which is root 3 a by 2 x cap plus a by 2 y cap, dot product with b1 vector, and b1 vector we have calculated, and b1 vector came as 2 pi by root 3a x cap plus 2 pi by a y cap divided by, we have to take the modulus value of this. The modulus of b1 vector will be equals to root 3a by 2 whole square plus a by 2 whole square, and mod of b1 vector will be given by 2 pi by root 3a whole square plus 2 pi by a Alright, so this is how we calculate the angle, taking the dot product divided by the magnitudes. Now here if you take the dot product, so what we get, we will get okay, so now here x dot x we know will be equals to 1, while the x dot y terms will be 0, so I will not write the x dot y terms. So what you will get here from here, or let me just write everything once. So I will get pi times x cap dot x cap, and then I will get 2 cancel root 3 pi x cap dot y cap plus this will be pi by root 3 y cap dot x cap, and I will also have this okay, let me just write it, this is going outside. Okay, root 3 2, it will be pi times x cap dot pi times x cap dot x cap plus this will be pi by root 3 and x cap dot, okay, this is x cap dot x cap, and this will be, if I do x cap dot y cap, it will be root 3 pi times x cap dot y cap, and y cap dot x cap term, that will be a by 2 can cancel, pi by root 3 y cap dot x cap plus you cancel out to do just pi y cap dot y cap. Alright, divided by this value, it will be 3a square by 4 plus a square by 4. So from here the modulus value root 3 a square by 4, and this is root 3a by 2 will be 3a square by 4 plus a square by 4, which is 4a square by 4, which is root a square, so it will be just a vector, and we know that the magnitude of a1 vector is just a. And while if you do this, it is 1 by 3a square, 2 pi you can take out common to solve this part. You can just take out 2 pi common from here, to the power 1 by 2, sorry, I didn't put power 1 by 2 here, let's just put 1 by 2 here. Alright, and here I have taken the square root, or you can take the power 1 by 2, you can just set the power 1 by 2. Alright, so that will be this will be 3a square by 4 plus a square by 4 1 by 2. Okay, this part, that will give you just a, which is the magnitude of mod of a1 vector, and mod of b1 vector, that will be equals to 2 pi, you can take them out, 1 by 3a square plus 1 by e square. So you can say it will be 4 by 3a square, and so that will be, so that magnitude, so one magnitude will be a, and this magnitude will be equals to 4 pi by root 3a. Okay, so you can just calculate it. It will be let me just solve it quickly. So it will be 4 pi square by 3a square plus, let me just calculate it quickly, 4 pi square by 3a square plus 4 pi square by a square to the power 1 by 2, and I am solving this part. So you just take the 4 pi square common, and we have 3a square will be 1 plus 3 to the power 1 by 2, 3 plus 1 will be 4, and it will come outside 2 divided by root 3a. This gives you 4 pi by root 3a. Alright, so this is your mod of b1 vector. Let me just cut it out. Alright, and so and also if we solve it, x cap dot x cap will be 1, if you do y cap 0, y cap dot x cap 0, and this will be 1. So what we are left with? We are left with pi plus pi will be 2 pi, and this will be 4 pi times root 3. So what we are getting is here is we are getting 3 by 2. So what we are getting here, cos theta is equals to root 3 by 2. Therefore, let me just write it here. So this implies cos theta equals to root 3 by 2, and therefore theta will be equals to 30 degree. Okay, because cos 30 degree is, we know cos 30 degree is root 3 by 2. So by this we have calculated our this angle between those two is 30 degrees. So last time I just brought it, and that 30 degrees is the angle between v1 vector, and this time we have calculated it as well. Alright, so let's just go to the C part that we have not done yet. So the C part was describe and sketch the first Brillouin zone of the hexagonal space lattice. Okay, so now we have to sketch, describe and sketch the first Brillouin zone for the hexagonal space lattice. So what? We know that our reciprocal lattice looks like this. So so what I will do the same. Okay, so for this C part, we will form this hexagonal space lattice. So I will not draw the C axis. C axis you can just cut and think that you just take the half along the C axis, and that will just give you the volume for the 3D. So I will just draw the reciprocal lattice in 2D only. So first let me draw it in 2D, and then we have these points. We have one point here, one point here. We have one point here, one point here, and we have one point here, one point here. Okay, so this is, I guess, our reciprocal. So I'm just drawing the reciprocal lattice, and I have a b1 vector, b2 vector, and this are my joining lines, and at the center also we will have one point. This is our hexagonal lattice in this, and let me just draw the b1 vector and b2 vector. These are your vectors. Okay, so let's say, so this is your b1 vector and this is your b2 vector. Okay, similarly there will be a minus b1 vector. So this is your minus b1 vector, and this will be your minus b2 vector. And then these lattice points, they will also some combination of this you can check. This will be like b1 vector minus b2 vector, and this will be b2 vector minus b1 vector. So by this you will get this lattice point as well. So these are the nearest. We have just joined the this lattice points, and now we know that to get the Brillouin zone, what we have to do, we have to take the perpendicular bisector for each one of them. So let's say that we draw the perpendicular bisector for this vector. Then I will draw a perpendicular bisector for this lattice vector. Then I will draw a perpendicular bisector for this lattice vector. Then I will draw perpendicular bisector for this lattice vector. Then I will draw perpendicular bisector for this lattice vector, and then the perpendicular bisector for this one. So it is approximately I have drawn the this perpendicular bisector, and this region, which is enclosed by this perpendicular bisector. This is our Brillouin zone. Right, so this is our first Brillouin zone, and in the C axis it is just like B3 will be in the perpendicular. So if you just draw a C vector which is perpendicular to this center point, then that will be your B3 vector, and then you just have to take a perpendicular vector, and then you will have a minus B3 vector as well. So you just draw for a 3D. I cannot show here, but you just have to draw an upward and a downward B3 vector. Draw, okay. B3 vector. So let me just mention it here. Draw B3 and minus 3 out of plane and in plane, and take perpendicular bisector of them to get the Brillouin zone in 3D. Okay, so you have to just take these perpendicular vectors, okay, B3 vector, and then you have to draw those and take the perpendicular this thing. So this will be just this will just be extended in 3D. Okay, so for 3D part I am not showing, but for in the 2D plane we can see this. This is how the Brillouin zone will look like. Let me just explain it, what we have done here. Okay. Now 6 vectors So I guess for the 3D vector, maybe you have to take B3 vector minus B3 vector and take the perpendicular bisector, and then you have to basically project it. So for 3D, we are just not discuss the 3D part. Okay? So we are just doing a 3D part, but basically you have to take some B3 minus B3, and then in the 3D also there will be like the projections of these points will also be there by some B3 vector. So you have to take those combinations, but we are just showing the building zone in D2D plane only. In 2D plane. This is the first building zone in 2D plane. So 6 vectors. So let me just explain it. 6 vectors in the reciprocal lattice are shown as red line, green lines. The broken lines, the broken blue lines. Six vectors in the reciprocal lattice are shown as green lines. The broken lines are the perpendicular, the broken blue lines, are the perpendicular bisectors at the midpoints. The inscribed hexagon forms the cross section of the horizon zone in XY plane. Sweep the shaded. Okay, so this is sweep this shaded area along z-axis from z equals to minus pi by c, because so that will be our so b3 vector. We know that our b3 vector is basically that was same. b3 vector is 2 pi by c. So you will have b3 vector upward, b3 vector downward, and here you have to take a perpendicular vector, that will be plus pi by c and minus pi by c. So I have written, I guess, something similar, but here I have explained it in a much better way. Shift the shaded area along z axis from z equals to minus pi by 6 to z equals to pi by c. Okay, so these are the perpendicular bisector for minus b3 and b3 vector respectively. Okay, so using this we get the whole first brilliant zone. This is what we find. Brilliant zone for the first. So we have
first Lorentz zone. Okay, note that and then here note that the first Lorentz zone of the hexagonal lattice is also a hexagonal structure.
Alright, so this is also a similar hexagonal structure because it's a hexagon and then you just sweep it from minus pi by c to pi by c. Alright, so this was our alright, so this is how we have explained the first Lorentz zone. So this was our part C, which was remaining. Now let's quickly go to problem number 2. So problem number 2, this is from Ashtot Mamme and this is for I guess week 3 part. It is regarding the Fermi-Dirac Statistics. So let's just find it. Alright, so problem number 2, that is taken from Ashcroft and Marmin chapter 2, and we are solving its problem number 3 part A and B only. So the problem is that we have to determine the classical limit of the Fermi-Dirac statistics that we have studied. So we know that from the Fermi-Dirac distribution reduces, it is explained here that the Fermi-Dirac distribution reduces to the Maxwell-Boltzmann distribution, provided that the Fermi function is much less than unity for every positive epsilon. Okay, so if the provided the Fermi is much less than the unity value for every positive function, for in that case our f epsilon becomes this, and the necessary and sufficient condition for this to hold is that e to the minus mu by kbt must be much greater than 1, and then we have to provide some. So let me just show you what this first point tells us. So what is this first point is telling us that we know our Fermi-Dirac distribution, that is given by 1 upon 1 plus e to the power epsilon minus mu divided by kbt. Alright, this is our Fermi-Dirac distribution, and for epsilon for e to for e to the power mu by kbt much greater than 1, so for e to the power minus mu by kbt is much greater. So if e to the power minus mu by kbt is much greater than 1, then what will happen is that our f of epsilon, and that is what it is arguing, the problem is reduce the positive provided the Fermi function is much less than the unity for every positive integer for every positive epsilon energy. This is much if this value is much less than 1. So basically what we can do, we can approximate our f of epsilon now to 1 upon e to the power, because this minus mu by kbt is very large value and e to the power epsilon by kbt is again a positive value. So overall that term will be very large than the unity. So what we have, we can just write 1 upon epsilon minus mu by kbt. We can ignore the plus 1 in the denominator, and this gives us our Fermi-Dirac distribution at e to the power minus e by minus mu kbt, and thus this is our Dirac distribution actually. This is our Boltzmann distribution. So our Fermi-Dirac distribution becomes Boltzmann distribution if this condition is being satisfied. Alright, so let's go to part A. So this is what has been given to us. Now we have to solve some part A and B. So in part A, it is saying that assuming 2.104, which is this condition. So it is saying that 2.104 holds. Okay, so this condition holds that we are talking about. Show that this RS value, okay, RS we have defined earlier as well, which comes from the volume for an electron. Let me say how much space it occupies. We have to show that this RS value is given by this kind of complicated formula. In conjunction with 2.104, this requires that this RS value from this
equation, this RS value also has to be greater than this, which can also be taken as the condition for the validity of classical statistics. Okay, so the C and D part we are not going to do, we are just going to do A and B part only. And then in the B part we have to find what is the significance of the length RS must exceed. Okay, now for this part, A part, we have f of epsilon is given by e to the power minus epsilon minus mu by kBt. Alright, now we know that 1 by n, where n is the, we know n is our number of electrons per unit volume, that is equals to 4 by 3 pi rs 4 cube, where n is our electron density and this rs is the radius of the spherical volume occupied by a single electron. Alright, so in that from here, from this formula we know RS, I can write RS as 3 upon 4 pi n whole to the power 1 by 3. Alright, this we can, therefore we can write RS as this. Now we know our energy N is given by 2 times, which is for considering both spin up and spin down, dk vector divided by 8 pi cube times f of epsilon of k vector. Alright, and now this I can, this is 2 times this, so this I can write it as 4 pi k square dk divided by, we have 8 pi cube, and we have our f of epsilon, and f in terms of epsilon we have. So now from here what we are getting, we are getting our integral, our cancelling of stuff. We will have k square dk divided by pi square times f of epsilon. Now we know epsilon is equals to h pi square k square by 2m. Alright, this is for the free particle case. We have k is equals to under root of 2m epsilon upon h pi square, where k is this. So basically we have d epsilon is equals to, if you do d epsilon, we have 2k, d epsilon will be equals to h pi square times 2k dk divided by 2m, and then you can do this cancellation here. So from here what we will get is k dk will be equals to m upon h cross square times d epsilon. Alright, and now therefore this implies our n will now be equals to, we will replace this value, so instead of k square k dk we can write this, instead of k we can write that. Okay, so we have 1 upon pi square, okay, and instead of k I will write under root of 2m epsilon upon h pi square, 1k I will write this, and for k dk, okay, there will be 1k and 1k dk, I can write m upon h pi square times d epsilon, and I have an f epsilon, so let me just write f of epsilon times d epsilon. Okay, so after doing some more manipulation, what we will have at the end is, and our energy value will go from 0 to infinity. I will have this d epsilon m upon pi square h pi square times under root of 2m epsilon by h pi square times e. Now our f epsilon, we have to use our f epsilon as given here. Okay, we are considering this condition is holding true. Okay, so this condition is holding true, so that's why we are using this. So our f epsilon has now changed, and it will be equals to e to the power minus epsilon minus mu by kBt. Okay, so this is what I have. Now I have to solve. Now I have to solve this integral. f of epsilon is given to us like this. Okay, now I have to solve this integral. So for that, what I will do, I will take out first I will take out the common terms from the integral, and m square phi square h phi square under root of 2m h phi square integration from 0 to infinity. I will have d epsilon under root of epsilon e to the power minus and also of here, and also I can take out this as e to the power nu by kbt, and integration will from 0 to infinity d epsilon under root of epsilon e to the power minus epsilon upon kbt. Alright, now to solve this integral, what we do, let x is equals to epsilon upon kbt, which implies I can write epsilon as x kbt, and from here dx will also equal to d epsilon by kbt, so I can write my d epsilon as kbt times dx. Replacing those terms there, what we will have m upon phi square h phi square times 2m upon h phi square whole to the power 1 by 2 e to the power mu by kbt. I will have now x also will be 0 at epsilon 0, it will be infinity. For epsilon infinity, I will have dx instead of d epsilon, and I will have kbt times of dx here, and kbt. Okay, so this and also we have under root of epsilon as well, so we did kbt by 2, and this is kbt, so overall I will have kbt to the power by 2 x to the power 1 by 2. Okay, and we have e to the power minus x. So we have taken e epsilon by kbt, which was in the exponential, we have taken that as x. Alright, and to solve this problem, we have n is equals to m upon phi square h phi square. This will be 2m upon h phi square whole to the power 1 by 2, taking kbt to the power 3 by 2 form. Okay, so this I can take out of the integral. Alright, and then and e to the power nu by kbt, that is also out of the integral, and then we have integration from 0 to infinity dx times under root of x e to the power minus x. Now this is called gamma function. So this is a complicated integral, so you don't have to solve it. Only if you get this question, you are given this integral. This is called a gamma function. Okay, this is by gamma of z. Okay, and this gamma of z has its definition, which is 0 to infinity g of x to the power z minus 1 e to the power minus x. Okay, so you can see that here our z is here z is equals to 3 by 2 minus 1 will be half. Okay, so here z is equals to, so here what we have here, z is equals to 3 by 2, so we have gamma of 3 by 2, which will be equal to 0 to infinity dx x to the power 1 by 2 e to the power minus x. This is our integral, and that will be equals to half of gamma of 1 by 2, and gamma of 1 by 2 is equals to root pi, so it is root pi by 2. Okay, so this is the definition. Most likely if this kind of question is given to you, then that we provided to you. So we can write our n here as m upon phi square h phi square times 2m upon h phi square whole to the power 1 by 2 kbt to the power 3 by 2 e to the power mu by kbt times this gamma function will be equals to under root pi by 2. So our n will be here equals to, after little bit manipulation, we have 2m upon h phi square whole to the power 3 by 2, 1 upon 4 pi to the power 3 by 2 kbt to the power 3 by 2 e to the power mu by kbt. Alright, so and now we have the n value, so now we can find out rs. Okay, we find out rs, and our rs was equals to 3 upon 4 pi n. So this is our n, so let me just mark it like this. Okay, this is our n, and now we just need to find our rs, and rs equals 3 upon 4 pi n whole to the power 1 by 3. This was our rs. So just put these values here. I have 3 upon 4 to the power 1 by 3, 1 by n to the power 1 by 3. So that is equal to h5 square upon 2m to the power now 1 by 2, 4, and then we will have 4 to the power 1 by 3 and 5 to the power 1 by 2 divided by k dt to the power 1 by 2, and it will be e to the power minus mu upon 3 kBT. Alright, so from here we have our rs will come as e to the power minus mu upon 3 kBT times 3 to the power 1 by 3 pi to the power 1 by 6. Okay, this is just this manipulation. If you do 1 by 2 minus 1 by 3, 1 by 6 h cross times 2m kBT. Okay, 2m kBT to the power minus. Okay, so this will be our rs, and if we just check with our result, rs e to the power minus 2 by 3 kBT to the power 1 by 3 pi to 1 by 6 h square 2m kBT to the power minus 1 by 2. So we have proved that rs will be equal to this, and also since this e to the power minus nu by kb, we have to solve one more relation as well, and it is given that this relation for Fermi-Dirac distribution works like Boltzmann distribution. This we have shown that there is given that, and we have also seen it, that e to the power minus nu by kBT has to be much greater than 1, which implies e to the power minus nu by 3 kBT. So e to the power minus nu by 3 kBT will be greater than e to the power minus nu by kBT, so this will also be much greater than 1. Okay, because since e to the power minus nu by 3 kBT is greater than e to the power minus nu by kBT. Right, so this implies if I do rs upon these this all the other rs upon h cross square by 2m kBT okay, so this term rs upon h square upon 2m kBT, that is from the rs equation, that comes as 3 to the power 1 by 3. Okay, so here I can take this h cross square here because I have 2m kBT rs upon, so I am taking a square on that side, h cross square to the power 1 by 2. This will be rs upon h cross square divided by 2m kBT whole to the power 1 by 2. Okay, so I am just taking 2m kBT 1 by 2 here on the left hand side, and h cross is also there, so h cross square to the power 1 by 2 will become n to the power 1 by 3 pi to the power we have 1 by 6 e to the power minus mu upon 3 kBT. Now since e to the power minus mu upon 3 kBT is much greater than 1, so 3 to the power 1 by 3 power 1 by 6 is of some constant, so that will also be very much greater than 1, which implies that our rs upon h square upon 2m kBT to the power 1 by 2, this must also be much greater than 1, which implies that rs must be much greater than h cross square by 2m kBT to the power 1 by 2. So this is like the lower limit we have found on rs, like rs has to be much greater than h square by 2m kBT to the power 1 by 2, and that was the second part of this part A. Like we have to also show that rs will be greater than h square by 2m kBT to the power 1 by 2. Alright, this is the condition for the validity of classical statistics. So if our rs comes as much greater than this h square upon 2m kBT to the power 1 by 2,
then we can use our, instead of Fermi-Dirac statistics, we can use the classical statistics, which is the Boltzmann Maxwell-Boltzmann distribution. Now in the B part, it is asking what is the significance of the length Rs must exceed. Okay, now what is the significance of this Rs value that we have found? Now here Rs is defined as the radius of the sphere whose volume is equal to the volume per conduction or per electron if Rs increases, it means that per, again you can say per conduction electron. So if we are talking about metals, conduction, we are talking about this in case of metals, conduction electron. It means that the conduction electron density and I have written here n is the free electron density. Okay, let me just carry that with the free electron density. Electron density decreases. Okay, so this we know earlier as well, it is inversely proportional to the electron density, and we are also saying that if Rs is defined as the radius of the sphere whose volume is equal to the volume per conduction electron, this is the definition of Rs. And if Rs is increasing, because we are saying that Rs must be much larger than this minimum value, then it means that the conduction electron density is decreasing. So we are decreasing the conduction electron density at temperatures higher than the temperature at which condition, let me call this condition 1 is satisfied. Okay, so the temperature, so if we keep increasing this temperature, then this Rs value will be, okay, S square by 2 mkBT will decrease, and thus our Rs value will start higher than this. So the temperature, so we will increase the temperature to get the condition 1, and at temperature higher than the temperature at which condition 1 is satisfied, it is clear that Rs is also large and electron are more free to move. Okay, so Rs will be large, and Rs is basically the volume of this conduction electron. So the conduction electron is now occupying a very large volume. They are more free to move. S square upon 2 mkBT to the power by 2. It implies Rs so the electrons are more free to move. So if Rs is much greater than, so for temperatures where this Rs is for temperature higher than this Rs, where it satisfied this condition, that H square by 2 mkBT, it means that Rs is much greater than your 1 by k, where k is the wave vector,
energy E is given is okay, at very high temperatures we can consider, we are basically going to the Boltzmann distribution. We are seeing the electrons are behaving like the classical particles, so our energy will also be approximately equals to kBt, which will be equals to h square k square by 2m. So which implies our k, which is our wave vector, it will be approximately equals to 2m kBt to the power upon x square to the power 1 by 2. Alright, so this Rs that we have found, it is basically 1 by k at in the classical limit, when we are going to very high temperature where this condition is satisfying, and we are getting the Boltzmann distribution instead of the Fermi-Dirac distribution, which defines this motion of the electrons. This probability of finding an electron everywhere, so that is more defined by the Boltzmann distribution. So in that case, basically what is happening is our Rs is becoming much greater than our wave vector. So it implies that is the interparticle separation is larger. So Rs, you can take Rs as the kind of interparticle separation, because Rs is basically the radius of the volume where our electron is moving, a single electron moving. So it implies that if the interparticle separation is larger than 1 by k, we can consider it as in classical state. So that is the significance of solving for this Rs. So we have find this condition that if our interparticle separation, let's say interparticle separation like electrons which are obeying the Fermi-Dirac distribution, if it is larger than 1 by k, then we can consider it as in classical state. Here k can be considered as the d Broglie wavelength. Right? Okay, so if it is larger than this d Broglie, is considered k can be considered as the d Broglie wavelength. Okay. Can be considered as d Broglie wave. It will be like k equals to 2 pi by lambda basically. So k is not so you know d Broglie wavelength, lambda is equal to h upon p. Okay, so you just have to calculate this lambda, and your k will be given by, can be considered from d Broglie wavelength, where d Broglie wavelength lambda is h upon p, and our k will be equal to 2 pi by lambda. Okay, so this is how we can consider it like this. So basically what we are saying is that if the interparticle separation is larger than this d Broglie wavelength, then we can say that the particle it will be in the classical state. Alright, so let's go to problem number 3 now. So now we will solve some problems regarding week 2 and week 1 and week 2 contents, you can say. The problems are mostly regarding the particle in a box problem. So this problem number 3. It is from Griffith's Introduction to Quantum Mechanics, chapter number 2. So what is given to us? We have a particle in the infinite square well. Alright. So what we have in this question: a particle in the infinite square well has as its initial wave function an even mixture of the first two stationary state. Okay, so we have a particle which has we can say the initial wave function is an even mixture of first two stationary state e times psi 1x and psi 2x. Okay, so they have the same
amount of 7x and psi 2x we have mixed to and that is our initial state. Now first, and we have several parts to solve. Now the first part is we have to solve normalize the psi x comma 0, that is find the value of a. Okay, so let us start with this. So for the part A we have to normalize this. So we will find the mod of psi square, which is equals to psi times, which is basically psi star times psi, and that will be equal to, and this is our psi function is real, that will be equal to mod of a square psi 1 star plus psi 2 star, because a times a star will be mod of a square times psi 1 plus psi 2. Alright, now this will be equal to mod of a square times psi 1 star psi 1 plus psi 1 star psi 2 plus psi 2 star psi 1 plus psi 2 star psi 2 psi 2 star psi 2. Yeah. So here what we have mod of a square. Now this I can write it as psi 1 square plus psi 2 square plus or this two terms will be same, so it will be 2 times psi 1 psi 2 plus psi 2 square. Why? Because since psi 1 and psi 2 are real. Okay, we know that this psi 1 psi 2 wave function are real for our case, which is a particle in a box, infinite spiral well. That's why we can just write it like this. Now to normalize, we need indication of mod of psi square dx, that has to be equals to 1. So mod of a square psi 1 square plus psi 2 square plus 2 times psi 1 psi 2 dx will be equals to 1. Now since psi 1 and psi 2 are orthonormal, okay, we know that they are orthonormal, so integration of psi 1 psi 2 dx, there will be equals to 0, and integration of psi 1 square dx will be equals to, and integration of psi 1 square dx will be equals to 1, integration of psi 2 square dx is equals to 1. Okay, I am not writing psi 2 of x because it is already implied. So by this what we will get 2 times of mod of a square equals to 1. So if you get, so the integration by 7 psi 2, that will be 0. Let me just right, so what we have is mod of a square times integration over 7 square dx plus integration over psi 2 square dx plus 2 times integration over psi 1 psi 2 of dx. And here we have written this, so this 7 psi 2 integration, this will be 0, this will be 1, and this will be 1, and this we have shown this has to be equals to 1. But for normalization, so we have mod of a square, 2 times mod of a square will be equals to 1, which implies our a will be equals to 1 by root 2. So this is our normalization condition. So that is, so we have normalized and find the value of a. Now in the B part, it is asking us find psi x comma t, and this priority density mod of psi x comma t whole square. Express the latter as a sinusoidal function of time as an and so consider the result, and we have given that we can consider omega is pi square h cross upon 2 m square. Alright, so let's just solve for part B. We have to find psi x comma t and the priority density as well. Now we are given as psi x comma t. So psi x comma 0 is given to us, initial state is given to us. So how we can write psi x comma t? We can write simply psi x comma t as 1 by root 2, which is our a. I will have psi 1 of x, psi 1 of function, times e to the power minus iota e1 t by h cross plus psi of 2 e to the power minus iota e2 t by h cross. Okay, so if I have to find the time dependent wave function, I have psi x comma 0, and for psi 1 psi 2 these are the eigen function for this different wave function. So we can write this e1 e2. Okay, and remember that here En is equals to n square h square pi square h y square n square pi square h y square by 2 m a square. Alright,
n square pi square x square by 2m square, if you remember, that was solution. And it is given as omega we can take as this, which is pi square h cross upon 2m square. Okay, so let omega is equals to pi square h cross upon 2m square, pi square h cross upon 2m a square. Okay, pi square h cross upon 2m a square. So in that case our En is equals to n square h cross omega. Okay, because pi square h cross omega square will be this, so this is our En, and this implies our E1 value will be equals to h cross omega, and our E2 value will be equals to 4 times h cross omega. Okay, now we just have to put these values here. So our psi x comma t will be equals to 1 by root 2, and also on what is our sin n function as well. We also know that, and also here sin n of x is equals to under root 2 by a sin n pi x by a. This is our formula. So our psi 1 will be equals to under root 2 by a sin of pi x by a, and our psi 2 will be equals to under root 2 by a sin 2 pi x by a. Right? So our psi x comma t will be equals to, so this implies our psi x comma t will be equals to 1 by root 2 times psi root 2 by a sin pi x by a times e to the power minus iota. E1 is equals to here h cross omega t by h cross, so it will be just e to the power minus iota omega t plus under root of 2 by a sin of 2 pi x by a e to the power minus iota, it is 4 omega t. Okay, it will be 4 omega t. So what I will do, I will take this root 2a e to the power minus iota omega t, that will be taken common. So what we have psi of x comma t will be equals to, if I take under 2 by a, those things cancel out. We have left with 1 by under root of a e to the minus iota omega t times sin of pi x by a plus sin of 2 pi x by a times e to the power minus iota. We have 3 omega t. We have taken one e to the power minus iota omega t, so we are left with 3 omega t. So this will be our answer. Okay, psi of x comma t is equal to 1 by root of a to the minus iota omega t sin pi x by a plus sin 2 pi x by a to the minus iota 3 omega t. Alright, now we have to find mod of psi x comma t whole square, which is basically psi star x comma t times psi of x comma t. Okay, we just have to take the complex conjugate. So that will be equals to, now if you take the complex conjugate, so 1 by root a, so let me just write psi, so this will give me, this term will be equals to 1 by root a e to the power iota omega t will be sin of pi x by a plus sin of 2 pi x by a e to the power iota 3 omega t. Okay, so all the iota terms will become will change their sign. So 1 by root a it so we have this is our psi star x comma t. So complex conjugate, you just replace all the iota terms. If you take the whole complex conjugate, all the iota terms will change their sign, so minus will become plus, and again we have the same thing, e to the power minus iota omega t, which is psi x comma t, what we have formed, sin of pi x by a plus sin of 2 pi x by a e to the minus iota 3 omega t. Okay, now we just when we multiply these two, we get 1 by a and e to the power iota omega t times e to the power minus iota omega t, that will be 1. And then we will just multiply these boxes. So what we have sine square pi x by a plus similarly we will have a sine square 2 pi x by a, where e to the power iota 3 omega t times e to the power minus iota 3 omega t will be 1. And then the cross terms we will have I will take this 2 common. Sine of pi x by a and sine of 2 pi x by a times e to the power iota 3 omega t plus e to the power minus iota 3 omega t. Right? So this will be our term. Okay, this will be the cross terms. If you multiply this, this will be this cross terms. All right, that will be given by this. Now we have to use e to the power iota theta is equals to cos theta plus iota sin theta. Right? So that gives us mod of psi of x comma t whole square will be equals to 1 by a sine square pi x by a plus sine square 2 pi x by a plus, so this will be cos of 3 omega t plus iota sin 3 omega t. Similarly, cos of 3 omega t minus of 3 omega t, which is just cos of 3 omega t minus iota sin 3 omega t. Okay, so this will, just open this, cos of 3 omega t plus iota sin of 3 omega t plus cos of minus 3 omega t minus iota sin of 3 omega t. Alright, so this plus this 2 will just cancel out because minus will go out, and this minus of this will be just same, so it will be just cos 3 omega t. So we get this 2 times of sine pi x by a and sine 2 pi x by a. Alright, times cos of 3 omega t. Alright, so this will be our answer for our mod of psi x comma t whole square. G1 by a sine square pi x by a sine square 2 pi x by a 2 times sine of pi x by a sine 2 pi x by a times cos 3 omega t. Alright, so now let's go to part C. So in part C it is asking compute the expectation value of x. Okay, note that it oscillates in time, and what is the angular frequency of the oscillation, what is the amplitude of the oscillation. And also, like, it is written sarcastic. Okay, if your amplitude is greater than a by 2, then you should go directly to J. Okay, so let's just see what we will get on our answer. So now we know expectation value of x. Okay, so let's find expectation value of x. And expectation value of x is given by here x times mod of psi x comma t whole square dx. Alright, so here we have found this mod of psi x comma t whole square. So you can just do the calculation. X and integration will be from 0 to a. Okay, it is an infinite square wave from 0 to a, and that's why this oscillation could not be greater than a by 2. That you will see. It will be sine square pi x by a plus sine square 2 pi x by a plus 2 times sine of pi x by a sine of 2 pi x by a cos of 3 omega t. Integration of dx. So we will just write integration here. 0 to a dx times x.
Okay, 1 by I have already taken out of this out of x comma d square because it is independent of x. Okay, so now we have this big integral problem to solve. So let me write again. So my expectation value of x will be equals to 1 by a times I have to solve the integral when is 0 1 if I just multiply x here it will become 0 to a. I will have dx x times sine square pi x by a plus relation 0 to a dx x times sine square 2 pi x by a. Okay, so let me just go down here. Okay, integration from 0 to a dx x times 2x times sine of 2 or maybe just write it here itself plus integration over 0 to a dx times 2x sine of pi x by a sine of 2 pi x by a times cos of 3 omega t. Okay, so this is our integration, and here we can see that we basically have to solve this three integral. We have to solve this integral number I1, integral number I2, and this big and this integral number I3 to get our expectation value of x, and then we just have to do I1 plus I2 plus I3 1 by 8. Alright, so if you solve this problem, okay, now here so let me just so this could be solved. So this I1 I2 I3 this could be solved in similar fashion by integration by parts. So let me just solve the I1 value. So let us just solve all this I1 I2 I3. So my expectation value of x will be basically 1 by 8 times I1 plus I2 plus I3. Right, I1 plus I2 plus I3. So let me just solve this integrals. So first I will solve I1 value. So I1 is equals to integration from 0 to a dx times x sine square pi x by a. So what we can do first, we know 2 sine square theta, we know a formula. So I will multiply it by 2 and then divide it by 2. 0 to a, I will have dx x. Now 2 sine square theta is equals to 1 minus cos of 2 pi x by a. Okay, so I can write this as 1 minus 2 cos 2 pi x by a. So that gives me 1 by 2 integration from 0 to a dx x and minus 1 by 2 integration 0 to a dx x times cos of 2 pi x by a. Alright, now this will be equals to 1 by 2, it will be x square by 2. So from this integral you will get a square by 2. Alright, and this integral minus half, this we will solve by integration by parts. So I have solved integration by parts several times, so here right now I am not giving you the formula. So basically we will solve the integration by parts. So that will be equals to x times we will have x a upon 2 pi sine of 2 pi x by a from 0 to a and I will have a minus sign a upon 2 pi. We will do the integration of x, that will be 1. I will have a sine 2 pi x by a dx. Alright, now at the sign if you put a, so sine 2 pi, it will be sine 2 pi, it will be 0 0. So here this term will be 0, and this integral also if you solve it will give you a cosine function, and then it will give you a cos of 2 pi x by a. So this integral will be equals to a upon 2 pi cos of 2 pi x by a with a negative sign outside from 0 to a
and at cost, and which will be equals to basically minus a by 2, right, which will be basically equal to minus a by 2, cos 2 phi will be 1, cos 0 will be 1, so it will be overall equals to 0. So this term will also goes to 0. So overall the answer that we will get here will be just a square by 4. So I1 integral will come as a square by 4. And similarly you can check that this will be the same case for I2 as well. Only in I2 what we have sine squared 2 pi x by a. So what we have to do, we have to just put 2 here in each of them. Okay, so this dx will just come out same, and you can do the same integration. Okay, so and you can check that for I2 also, because it will be just, there will be sine square 2, there will be just more 2 here. There will be 4 pi x by a, where you have cos 2 pi x by a. Everywhere we will have cos 4 pi x by a, but we know that this integral will just goes to 0. Okay, either it is 2 or 4, it is an even value, that will also going to give you a 0. So you can check that I2 will also come as a square by 4. And regarding I3, now I3 integration, for I3 what we have here, I will take out 2 and cos of 3 omega t times, I have to integrate from 0 to a, x times sine of pi x by a and sine of 2 pi x by a dx here. Again for this it will be you can again use trigonometric you can again use trigonometric function of sine theta of 2 sine functions. Okay, and you can convert it into some other, and then again use the integration by parts. So I am leaving it for you guys to just try it out. So DIY. In case you have any problem, you can ask in the courses discussion forum, or later in the YouTube section as well if you have any problem with this integral. But overall, first for the time sake, and so it is similar. You have to find a trigonometric relation for this, for where you have a multiplication of sine, and then you will again have to use the same integration by parts. Okay, and the result that you will get is minus 8 e square upon 9 pi square. So I am just leaving it 9 now for just for the time sake. Okay, and you can also try out this integral. And so from here, our expectation value of x. So now we have all of these values. So our expectation value of x will just be equals to 1 by a I1 plus I2 plus I3. This was our value. So it will be 1 by a, and also the cosine function, sorry, this will be equals to times 2 times cos of 3 omega t. Alright, so it will be 1 by a times I1. Now I1 is equals to a square by 4, I2 is also a square by 4, and I3 is equals to minus 16 a square upon 9 pi square cos of 3 omega t. Okay. Let me just give you a hint. So to solve this thing, what you have to use is, you have to use that sine A times sine B is equals to half of cos of A minus B minus cos of A plus B. Alright, so this is the hint for you guys. Okay, so this is kind of the relation that we have used. So basically our equation will be half of, we will have 2 cosine function, cos of pi x by a minus 2 pi x by a. So one will be cos pi x by a and one will be cos 3 pi x by a, and then you just have to solve that integral and you will get this equation. Okay, so you can try it out yourself, and if you have any doubt, then it could be solved in the decision forum or in the YouTube section. Alright, so for the time sake, okay, so I have to go a little fast. So our expectation value now, a will come as a by 2 1 minus 32 upon 9 pi square cos of, okay, just and doing this calculation, cos of p omega t. Right, so this is our expectation value of x. So now the amplitude here, so our amplitude is basically equals to, so amplitude is the amplitude with the frequency, so it is not a by 2, it is with the whatever our oscillating function is. So our amplitude is basically here 32 upon 9 pi square times e by 2. That is our amplitude, and that will be equals to 0.3603 times e by 2. So here we can see that our amplitude is less than e by 2, so we don't have to go to GL. So as given in the Griffiths book, because our amplitude will come is coming less than a by 2. Okay, so this is less than a by 2. Alright, so yeah, we are safe. And then our angular frequency, okay, it was written that, if you remember in the question, it was written that you have to go to jail if your amplitude is greater than a by 2. So no, it is not it is less than a by 2, so we are safe here. And our angular frequency, that comes as that is coming as 3 omega, and it is 3 pi square, what is omega is just pi square h cross upon 2 m square. This is our angular frequency. So let's go to our D part, and our D part is the we have to find the we have to compute expectation value of the momentum, and as it is written very stylish, as Peter Rhodes would say, do it the weak way, easy way, Johnny. So basically the author wants us to do it the easy way. So what is the easy way? The expectation value of x, we can actually define this as, we know what is the momentum. Momentum is given by m dx by dt. Okay, so this will be m d by dt of expectation value of x. Okay, so we can use this easy way instead of actually going through all the integrations. So this is the easy way we can go to, and the expectation value of x we already have. So we just have to take this differential with respect to t, so that will be equals to a by 2 times minus 32 upon 9 pi square times, you have to say cos 3 omega t integral will be equals to minus 3 omega times sine of 3 omega t. So our expectation value of momentum will come as 8 h cross upon 3a. Okay, this is just a calculation, and we have put the value of omega here, which is sine of 3 omega t. So this you can check, we just put omega equal to pi square h cross upon 2ma square. Okay, and then you can just do the manipulation, and this is what you will get, omega t. Alright, and then the E part. So E part is, if you measure the energy of this particle, what values might you get, and what is the probability of getting each of them? Okay, so what will the values we get? So we just have 7 side 2, so we will get either E1 and E2. Okay, so when we get the expectation value of this with equal probability, and find the expectation value of, and also we have to find the expectation value of h cap, and how does it compare with E1 and E2. So for part E, if we calculate, if you measure the energy of, if you measure the energy, if you measure the energy of this particle, so basically this is a superposition of psi 1 and psi 2. So our particle, when we measure the particle, it will be either in the psi 1 and psi 2, and since it is equal contribution, so it will be equally will be there in psi 1 psi 2. So we will measure E1 and E2 with equal probability. Get either E1 equals to pi square h pi square by 2me square, or E2 equals to 2 pi square h pi square by me square with equal probability.
Okay, it will be equal priority because our this C constant is just A, and A is 1, A has come 1 by root 2, so the priority will be 1 by mod of A square, which is 1 by 2, priority of half for each one of them. And so our expectation value of, and then we have to find the expectation value of this Hamiltonian, which will be is equals to, so our expectation of value of a Hamiltonian, that will also come as just, so our expectation value of Hamiltonian will also be just the average of these energy values E1 and E2. So we don't need to calculate, so for this you don't have to calculate the expectation value of H cap exactly or doing the integration or anything. You just take the what is the probability with each one of them. So for the probability of with energy E1 it is half, and the energy E2 we can get with the same probability half, so it is basically half of E1 plus E2. Alright, so this implies our expectation value of H will be equals to, and E1 is this pi square H pi square by 2m, 2 plus 1 3, it will be just 3 by 2m a square, and 2 pi square H pi square by m a square, or let me just write it as 4 times pi square H pi square by 2m a square, so it will be just 5 by it will be 5 by 4, right? Yeah, 5 by 4 pi square H pi square by m a square. Okay, so this will be our expectation value, just the average of E1 and E2. And let's get the probability of finding energy E1 times E1 plus probability of finding E2 times E2. This is how. Now it's the so basically it is the average of E1 and E2. Alright, so this is the comparison with respect to E1 and E2. Sorry. Let's go to our problem number 4. How much time we have? Okay, we have just 30 minutes left. We are quite behind today. Alright, just 1 minute. Just a minute. Yeah, just have to check the recordings. Right. Okay, let's solve the problem number 4 now. So problem number 4, that is also from Griffith's Introduction to Quantum Mechanics, chapter 2. So problem number 2.8 of that chapter. So what it is asking, a particle of mass m in the infinite spiral well of its A starts out in the left half of the well. So our particle starts out from the left half of the well and is at t equals to 0 equally likely to be found at any point in that region. So this is the condition that is given to us. Okay, so what it starts from the left side of left half of the well, okay, and at t equals 0 it should be equally likely to be found at any point in that region. So the part A is what is its initial wave function psi x comma 0, and we have to assume it is real, and we don't have, and we have to normalize it as well. So according to the condition that is given, psi x comma 0 will be equals to, and is given that equally likely to be found at any point in that region. So we are saying is that our particle is in the left half only, and it is equally probable in that region. So I can write it as psi x comma 0 is some just constant a for x between 0 to a by 2, okay, because this mod of psi square will be give you the probability, and we want the probability to be constant for this x equals to 0 to a by 2 region. So our particle, according to this, our particle should be defined just by a constant a between this region from x equals 0 to a by 2, and it will be 0 for otherwise, okay. Otherwise, which is basically from our infinite spiral well, it will be from a by 2 to x, which is x from a by 2 to a. This will be 0. This is our initial wave function. Now we have to just do the normalization, which is mod of psi x comma 0 cos square dx. I am assuming that to be a real wave function, that has to be equals to 1. So it will be from 0 to a by 2 only, because otherwise a by 2 to 8 is 0. It will be just e square dx equals to 1. So what we have here is
a square times a by 2, that is will be equals to 1, which implies our a value will be equals to under root a by 2. Okay, so our initial wave function psi x comma 0 will be equals to, so our psi x comma 0 is basically equals to under root a by 2 for x between 0 to a by 2 and is equal to 0 otherwise. This is our initial wave function. And the B part is, what is the probability that a measurement of the energy would yield the value pi square h phi square by 2m e square. Okay, so it is asking what is the probability of that. Now we know En is equals to n square pi square h phi square by 2m e square. Okay, and here E is equals to pi square h pi square by 2m e square, that is given to us. So we need to find the probability that a particle, so we need, so which implies n is equals to, which implies n equals to 1 state. So we need to find the probability that our wave function our particle is in state psi 1 equals to root 2 by a sine which corresponds to your psi 1 function. Okay, sine pi square is equals to root 2 by a sine pi x by a. Okay, so when it is saying that the energy should be, the measurement should be this, it means that when we measure, the particle should have this energy, and the particle will have this energy if the particle is in our n equals to 1 ground state, because that is how the energy is matching. So we need to find basically the probability that our function is this. Now as we know, we can write our psi x comma 0 as summation over n cn psi n. Okay, and the probability to find psi 1, so therefore probability to find particle in state psi 1 is mod of c1 square. Okay, that is basically mod of c1 square. So from here we can write cn is equals to sin star psi of x comma 0 dx. This formula we know. So here our c1 equals to okay, so this is how we find this cn value. So we can write our any wave function as the summation over these eigenstate values of this particle in a box. And so okay, and the cn basically gives you the probability that a particle is in the state, and to find the probability particle in state psi 1 we have to need to find c1, and from here we can find c1 as, okay, now our sine function is given by root 2 by a sine pi x by a. Okay, and psi x comma 0 is basically under root 2 by a, and it is, the integration will be just from 0 to a by 2, because otherwise psi x comma 0 is equals to 0 times dx. This is the integral that we have to solve. So that we have at 2 by a, if you have to integrate sin pi x by a will be equals to a upon pi with a negative sign, and cos of pi x by a from 0 to a by 2, and cos a by 2 will be equals to cos pi by 2 will be 0, and cos 0 will be 1, so minus of, so it will be 0 minus 1. So what you will get is 2 upon pi. Okay, check it out. It will be 2 by a times minus a upon pi times 0 minus 1. Okay, so this will be equals to, this will give you 2 upon pi. So our c1 will be equals to 2 upon pi, and thus this probability, therefore probability to measure energy E pi square h square by 2m square, 2m square, which is basically 2e1, that is given by the probability p1, that is given by mod of c1 square, which will be equals to 2 upon pi whole square, which is equals to 0.4053. So approximately 40% of the chances that a particle will find a particle in the ground in n equals to 1 ground state of our infinite spiral web, and the energy value will be this. The value will be 0.4053. Alright, so let's go to our problem number 5 now. So in problem number 5, what you have to solve is, okay, a particle in the infinite spiral web has the initial wave function. Okay, we are given a particle in the infinite spiral web with this initial wave function psi of x comma 0 is equals to ax for x between 0 to a by 2 and a times a minus x for x between a by 2 to a. First we have to sketch the psi x comma 0 and determine the constant a. So let's start with part A. So my psi x comma 0 is a function of x I have to write, and here I have 0, this a by 2. Alright, so it will be my a by 2 distance a, because this is the partition that is given for boundaries that are given from a wave function. So my wave function given as it is a times x, so it is just a linearly increasing function up to a by 2. Alright, this is up to a by 2, and then after a by 2 its definition change and it becomes a times a minus x, so it is with the same minus a slope, and at x equals to a it is equals to 0. So my wave function will look like this. Okay, so from a by 2 initially the wave function at x equals 0 will be 0, and it will increase with the slope a, and then it will decrease with the slope minus a after a by 2, and at x equals to a it will be 0. So this will be our wave function. So we have sketched our wave function, and then we have to determine the constant a, which is we can obtain by the normalization. We will do mod of psi x comma 0 whole square dx, that has to be equals to 1. For this we will have 0 to a by 2. Our wave function is a square x square for this region, plus integration from a by 2 to a. Our wave function is a square a minus x whole square dx. This 4 has to be equals to 0. Right, now for this equation from here I can simply get it will be x cubed by 3 from 0 to a by 2, and for this what I will do is I will consider a minus x as t. I consider this a minus x as t. Okay, so it will be t square. Okay, for this integral let a minus x is equals to t, which will give you dx is equals to minus of dt, and x is equals to a minus t. Alright, so using that, okay, let me just write it here. I will get from this integral I will get a square times x cubed by 3 from 0 to a by 2, and for this integral using this definition I can rewrite this integral as equals to a by 2, this will be a by 2, and x equals to a, this will be 0. So integration will from now from a by 2 to 0, with a square times a minus x will be t square, and dx will be equals to minus of dt. Alright, since there is a minus of dt, so I can just change the integral sign here, the limits of integral, and I can write it as dt. So I guess this is easy to understand. This negative sign will just change the limits of integration, flip the limit of integration, and this should be equals to 1. Now this gives us a, so I can just take the a square common from both of sides. This will give me a cube by 24. Alright, this is just give me a cube by 24, plus this t cube will be this will be also this will be the same t cube integration t cube by 3. Okay, this will be also t cube by 3, and this will give me a cube upon 2 cube 8 here 24. This will also give you the same integral. This you can check. T square will be also t cube by 3. So what you will get a square times a cube upon 12. That should be equals to 1. which implies our a should be equals to, we take the square root, we get 2 by root 3 divided by a to the power 3 by 2. Alright, we just take this on 12 upon a cube a square and then take the square root. So this is our value of a, 2 by root 3 upon a to the power 3 by 2. Let's go to our b part. Now we have to find psi x comma t. Now psi x comma t, we just know that now to write psi x comma t, what we will do, we will write our psi x comma 0. We have to write our psi x comma 0 as summation of n cn times psi n of x, where sin n of x are our eigenstate of the infinite square well, where sin of x is equal to under root 2 by a sin n pi x by a, and we also have en is equal to n square pi square h pi square by 2m a square. This from the eigenvectors and eigenvalues of infinite square well. Alright, so and we know from here, we have already done in the previous one of the problem as well, the cn values are given by sin star psi of x comma 0 times dx. Okay, so now we need to find the cn values. Now here I will write cn as root 2 by a sin of n pi x by a, and psi of x comma 0, it is as we have defined here, it is actually sin x comma 0 is defined here, it is ax plus 0 to a by 2, a times a minus x plus 0 to a by 2, so it will be 0 to a by 2, it will be ax dx plus integration from a by 2 to a, under root 2 by a sin of n pi x by a, it will be a times a minus x times dx. Alright, so we have to solve these two integrals. Okay, so we have to solve these two integrals. Now I will take under root 2 by a is common to both of them. By capital A, I will take common to both of them. So I will have integration from 0 to a by 2 of sin of dx sin of n pi x by a, alright, times x, okay, times x also we have, plus I will have integration dx from a by 2 to a sin of n pi x by a, in this we have a minus x dx. Okay, and okay, so what I can do is, okay, I can write this as, actually I will put a minus x into this 2, so one will be integration a by 2 to a dx times a sin n pi x by a, and I will have a minus integration from a by 2 to a, and I will have an x sin of n pi x by a dx. Alright, because a minus x I can open and I can write this integral. Now again what we have this three integrals. We have this integral, let's say I1, we have, let's say, this integral I2, and we have this integral I3. So our answer, the Cn values will basically be equal to root 2 by a times capital A I1 plus I2 minus I3 minus so I can write this as a times of this. Let me just write it as a times of this I2. That will be a times of I2 minus of I3. Okay, so now we just have to calculate this I1, I2, I3. Now I1 is equals to, integration is given as 0 to a by 2 x times sine of n pi x a by dx Now this is similar to the what we have done earlier, so you just have to do it, use integration by parts. So I will just write the answer here in this case. So again we have to just use the same integration by parts. So I will just write the answer in this case. So you have to use the integration by parts. Use integration by parts. So it is basically integration over u dv is equals to ub minus integration over v du. Okay, this is the formula for integration by parts. So you just have to use this integration by parts formula, and we have already done a question the same thing in the previous question. So I will just write the answer in this case. That will equals to minus a square upon 2 n pi times cos of n pi by 2 plus a upon n pi whole square times sine of n pi by 2. So this is a DIY. So it will serve using this integration by parts, and it's a similar calculation, or only the integration limits have changed. So hopefully you should be able to solve it, and you should get this thing. Okay, minus a square upon 2 n pi cos of n pi by 2 plus a by n pi whole square sine of n pi by 2. And if you have any doubt, you can ask in the discussion forum or in the YouTube comments. Okay, then let's calculate the I2 value. Now I2 is we have to find integration from a by 2 to a. That is sine of pi sine of n pi x pi, right? And sine of n pi x pi. So this is just simple dx sine of n pi x by a. Okay, so that is very easy to solve. So that will be just you will have a negative sign minus a upon n pi, because sign will be minus cos, and we have cos of n pi x by a from 0 to from a by 2 to a at okay, so and you can find this value at a by, so this will just give you the I2 value will be just equal to from here, so it comes as a upon n pi, okay, cos of n pi by 2 cos of n pi by 2 minus cos of n pi, right? Cos of n pi by 2 minus cos of n pi. So this is a easy calculation to do. You can check it and do it. And then we have I3. Now I3 will be equal to again a by 2 to a. We have sine of, okay, I3 is a by 2 to a x times sine n pi x by a. N pi x by a times dx. Okay, again we have to use the same integration by parts, so you have to just use again the integration by parts. Use integration by parts. So again this is a DIY for you. You can try to do it, and if you find any issue, then you can ask later. Okay, I'm later in the decision forum or in the YouTube comments. Alright, so this is equals to minus a square upon n pi cos of n pi plus a square upon 2n pi cos of n pi by 2 minus a upon n pi whole square times sine of n pi by 2. Alright, minus a square upon n pi cos of n pi plus a square by 2n pi cos of n pi by 2 minus a upon n pi whole square sine of n pi by 2. So you should get this after integration. So from here we have finally have our Cn. So our Cn I was again under root 2 by a times capital A. Alright, and so we have the capital A. I'm putting it here right now. and I will write now I1. So just put these values of I1 and I2 and I3. So I1 is this big value minus e square upon 2n pi minus e square upon 2n pi cos of n pi by 2 plus a upon n pi whole square sine of n pi by 2. Okay, this is what you get, minus e square upon I1 minus e square upon 2n pi cos of n pi by 2 plus a upon n pi whole square sine of n pi by 2. This will be our I1. Then what we have I1 plus a times of I2 plus a times of I2, and I2 we have found is that it will be a times of, so it will be a times of a upon I2 is a upon n pi, so it will be a square upon n pi, a square upon n pi times cos of n pi by 2 cos of n pi by 2 and cos of n pi. So I2 has come as cos of n pi by 2. What we have is we have a minus sign of this, that's 3 times of I2. This is correct. So we have just had to do, sorry, I just getting confused, plus a times of I2, and a times of I2 it will be a square upon n pi, times cos of n pi by 2 minus a square upon n pi cos of what we have n pi, and then what we will have a minus of I3. We have a minus of I3, okay, because it's the formula is I2 minus of I3, and I3 we have calculated minus of a square upon n pi. Okay, I have to use minus of I3, sorry, this will be minus of I3, so it will be plus a square upon n pi cos of n pi, the same change of all the sign on I3, minus e square upon 2n pi cos of n pi by 2, and plus a upon n pi whole square sine of n pi by 2. So this will be our solution. And here after doing all the calculations, so I am just writing because we don't have enough time, so you just have to put the I1, I2, I3 like this, and many terms will cancel out here, and at the end what we will get, Cn is equals to 4 times of under root of 6 upon n pi whole square. So the terms which will cancel out, as you can see here, let me just show you what are the terms cancel out. So I will have minus e square upon 2n pi, and we have square upon 2n pi cos n pi by 2. Okay, so basically you have minus e square upon 2n pi cos n pi by 2 minus e square upon 2n pi cos n pi by 2, these two terms. Okay, so they will just add on, and we have a square upon n pi by 2. Okay, so they will add on gives you a square upon n pi by 2, and they will just cancel out with this thing. So you can just cancel out these three terms here. Alright, these three terms will get cancelled out. Sorry, not this one. So my mistake. We have a square upon minus a square upon 2n pi cos n pi by 2 minus a square upon 2n pi cos n pi by 2, and where we have a square n pi times, okay, this will be equal to minus a square upon n pi, and we have a square upon n pi cos n pi by 2. So we just cancel out a square upon n pi cos n pi by 2, and similarly we also have this minus e square upon n pi cos n pi and plus e square upon n pi cos n pi. So these two terms will cancel out with each other. So these three terms will cancel out with each other with green terms, and this red will cancel out with each other, and what we will get, we just write the, so what we will get, and these two terms will just add on. we have under root 2 by a times capital A times we will get 2 times of a square upon n square pi square times sine of n pi by 2. Okay, so if you use it, so basically the Cn value, okay, and if you do, okay, so from here what we will get finally get 4 upon root 6 by putting the value of a that we have found in our previous part. We will get n pi whole square sine of n pi by 2. Okay, so we just have to put the value of a, and this will be equals to, we can see it will be 0 for even n, and it will be equals to minus 1 to the power n minus 1 half 4 root 6 upon n pi whole square. This is for even n and this is for odd n. Okay, for odd n minus 1 to the power n minus 1 by 2 4 root 6 upon n pi whole square odd n. So this will be our Cn values. Now this implies our psi x comma t will be given by 4 under root of 6 upon pi square under root of 2 by a. Okay, so for even and this our side, so there will be no contribution from the even eigenstate with even n, and the only contribution will be from the odd n ones 1, 3, 5 and so on, which is minus 1 to the power n minus 1 divided by 2 1 by n square and 1 by n square sine of n pi x by a e to the power minus iota e and t by h cross, where we know en will be equals to n square h by square pi square by 2m a square, and n is equals to 1, 3, 5 and so on. So this is our psi of x comma t. Right? Yeah. Alright, so this part is also done. Okay, let me just check how much time we have. Okay, we are already out of time, so unfortunately we are just going to solve this. Now we have to find so let's just complete this C and D part quickly. So what is the probability that a measurement of the energy would yield the value even? So that is similar to the what we have done earlier. So that will be just the probability will be just given by the mod of C1 square as we have done earlier, and if you calculate from here the mod of C1 square, we just have to put n equals to 1. Okay, we have the formula for Cn here, and we can get the, okay, here we have the formula for Cn. From here we can write C1, and that will become as 16.6 divided by pi to the power 4, and that will be equal to 0.9855. So here we can see that the even value is coming very good. It's not only 98%, so our system is most likely in the ground state only. And find the expectation value of the energy. Okay, and the expectation value of the energy, so as we have discussed in the previous question as well, the expectation value of this energy will be just the expectation value Hamiltonian v summation of n mod of Cn square times this En values. This will be given by 96 upon pi to the power 4 pi square h pi square by 2m a square. 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square, only the odd and are only contributing, and so on. And this summation, again this is just a series which summation comes at pi square by 8. Okay, so our expectation value of, so that will come as 48 times h pi square upon pi square ma square times pi square by 8. So our expectation value of h, which is the expectation value of the energy, comes as 6 h5 square by m a square. So it is 6 h5 square by m a square. That will be our expectation value. Although it is even value, which is h5 square pi square by 2m a square. Okay, so it is larger than that value. Although the ground the expectation it is coming 0.985, so our equation is mostly made up of our ground state, which should give you the energy 0.5 times. Okay, which gives an energy 0.5 to pi square 3 star 6. So it should give you an energy time 3 h5 square by m a square now, but it is coming at a larger than that because of the contribution from the state as well. Okay, so that is our part. So you can just check out this calculation. Okay, now okay, so this is we have more problem as well, but let me check. We are already out of our time, so unfortunately we cannot solve this problem. So most likely we will again I guess we will start with this code problem, and then we will try to cover other part as well in the next session. So let me just stop sharing. Alright, so we are at the end of today's session. So unfortunately we were just able to solve 5 of our previous numerical problems. So in the next session we will start with that 6th problem that I just shown you at the end. So we will start with that problem, and which is basically on the finding the expectation value of x square, momentum and momentum square, and the sigma x sigma p for the nth stationary state of the infinite square. So you have done this calculation using code, but we will just derive it analytically. And then in the next session we will try to solve all the programming problems from week 1 to week 5. So all the coding problems which were given in an assignment of this week 1 to week 5, we will try to solve them in our next session. And after that, if we have some more time, then we will try to solve some numerical problems for week 5 and week 6 as well in the next session. Alright, so thank you for your time.